So we ended Wednesday by trying to predict some of the products out of here. So I tried to provide these products and their appropriate stereochemistries all the way through. So you'll notice that in most cases, well, in all cases, we got two products, but in most we end up with enantiomers. And remember, the reason why is because a pi bond has those p orbitals. Our electrophile can either come in from the top or from the bottom, generating two potential orientations, two potential products. So that's what we got to watch out for. When we look at all four of these products, one should stand out as particularly different than the others for a variety of reasons, and that should stick hopefully with that lower left-hand corner. And the reason why that one should stand out is that we've got mercury in that structure. In all of the other three products, what we've got are covalent bonds, and in particular nonpolar covalent bonds. In the case of that last product here, we've got a mercury carbon bond, and that becomes a little bit dicier because we now have a metal-nonmetal bond. That is a tricky bond to deal with. So this can't possibly be the end of our reaction. We need to somehow get rid of that mercury, cleave it from our structure. And so that then pushes us to the next part. Okay, so in this case we broke it down and actually showed that we formed that three-membered intermediate with the mercuronium. The water comes in and attacks, we lose the hydrogen, and we end up with the alcohol added on one side, and we still have the mercury left on the other. So now the question becomes is, what do we add to help cleave and kick everything off of this and initiate this thing to go forward? And that becomes a little bit trickier to deal with, and we just kind of got to work with it the best we can. So, approaches to this. Short of memorization, this is going to be a hard one to nail down. Mercury is a weird transition metal, which means its chemistry is kind of all over the map. We could try and play electronegativity games, and that's going to be a hard thing to play. What will end up happening, for those of you that have actually memorized the reagents, is in our second step, what we will add is sodium borohydride. And the particular functionality out of our sodium borohydride is that it is hydride, it is supplying H-. That's relevant because what can happen is this H- can come in and kick the mercury out. Those are both double-headed arrows. Okay, which is kind of a neat process, and we would kind of leave it there, except since we're talking about the mechanisms, we're going to push it a little bit further and see why we need the borohydride. Okay, why do we need the boron? Why don't we just add sodium hydride? So number one issue, hydride is incredibly tiny, which means it is incredibly unstable and not very likely to act as a nucleophile. It would more likely act as a base. And that gets problematic because if it acts as a base, all it's going to do is react with the mildly acidic hydrogen on our alcohol instead of cleaving off the mercury. So we need something to stabilize that hydride. Boron just happens to be that molecule. Okay, so we need that strong nucleophile. To make it a strong nucleophile, something has to mitigate that wicked negative charge. That's what our boron's going to do for us. And I can't remember, do I have a nice picture? Yeah, we do kind of have a nice picture here. So, our sodium borohydride, we've got our general formula here. What we should remember that we've got the sodium as our metal, and then we have the BH4 minus. So BH4 actually carries a negative charge. If you go all the way back to the Lewis structure of boron, which we'll see here in just a little bit, boron is happy with only 3 groups of electrons. That means our hydride can come in. Give me a second here to clean up some space. Our hydride can come in as a negative charge, share its electrons fairly temporarily with the boron. We now have a relatively stabilized hydride, and we can use that in this next sequence of reactions. We're actually going to push this a little bit further with this process. Our negative is ultimately in these electrons. What those electrons need to do is kick out that mercury. We got to get rid of the mercury. So we can shuttle these electrons into the carbon. Carbon then has too many bonds, so we could potentially shuttle these electrons to the mercury. Here's where things get interesting. Mercury now has a glut of electrons. It might be nice if, say, there was some atom floating nearby that could potentially pick up those electrons. Say, like maybe boron. So if we get really careful with how we go through and draw this, what we end up seeing is that we have a four-membered transition state. Mercury, carbon, hydrogen, boron. This four-membered transition state is effectively a cycloaddition. We're adding hydrogen to one atom of our pi bond, if you will. In this case, it is a high-energy sigma bond. And we are adding boron to the other end of our high-energy sigma bond. So kind of a neat little process to go through and do that. The net result that we've always talked about before is now we've got our final product, and we kind of ignore what happened to the mercury and the boron, which probably not the greatest thing to do, but they aren't organic, so we kind of ignore them and don't stress because we've got our organic product and we can move forward. So what is happening with this tetra intermediate thing that is starting to get addressed with the borohydride, okay, which we just mentioned? Mercury, boron, hydrogen, carbon. So now what we want to do is push this a little bit further and say, well, what if instead of it being this weird mercury nasty craziness, is if we just straight up took it to a double bond? What happens under those circumstances? So before we even get into that, let's take a step back and look at our Lewis structure for BH3. So I'm going to give you a second to come up with the Lewis structure for BH3 and come up with a hybridization. So if you will, please press pause. That is all the time I'll give you, so we'll advance through here. And we've got our Lewis structure for boron. When we go through and apply that, what you should notice is that boron comes out as being sp2 hybridized. Okay, it only has three groups of electrons, which means we've got sp2 hybridization. There is a leftover p orbital on that boron. Well, that leftover p orbital has the potential to accept electrons, and it's that accepting of electrons that initiates the cascade when we're looking at the cyclotetra intermediate with an alkene addition in boron. Okay? This is similar to what we just saw with the mercury, but different. What we're now moving into is the addition reaction with boron. If we used BH4, that's going to be a problem because BH4 can't accept more electrons. Our alkenes are electron donors. So we have to differentiate. So what happens if we now take this compound and react it with 2Z-butene? And again, I'm going to ask you to take a second here, pause the video, draw out your 2Z-butene, and come up with a prediction on what should happen with BH3. So again, pause please, and that's the time you get. So we could now draw out our 2Z-butene. So we have our butene, 1, 2, 3, 4 carbons. We know it's an alkene because it says ene. So we got but for 4 carbons. Ene means we have an alkene, okay, or a pi bond. That pi bond is located at position 2, and we know that the arrangement is Z, which means cis or same side. With all that information, we can now draw the structure that we've got in front of us. So the initial Lewis structure may look like this. Not going to be particularly helpful for us in this case because what we're interested in what's happening with the p orbitals. So what I went ahead and did was drew that same structure, except what I did was took these carbon atoms and I pulled them up out of the plane at you. Okay, so that they are now wedged coming at you, hence those wedges. That then also means that the p orbitals, I'm going to clear everything for a moment here. The p orbitals that were on those carbons coming in and out of the board at you are now in the plane of the paper, so that's how we get this view. Why is this going to be helpful for us? Well, what happens when BH3 now gets near our alkene? Well, our alkene has those 2 electrons. Those electrons can shuttle up into a bond with the boron. Well, remember what boron did? It temporarily stabilized hydride, an excellent nucleophile. Okay? So let's just think about what's happening on charges. Okay? The boron reagent is now becoming this negative charge. What happened to our other carbon? Well, the other carbon over here lost electrons and is now positive. So we've got a really good nucleophile near a really good electrophile. The net result is that what we end up seeing, and this happens exceedingly rapidly to the point that it's a concerted mechanism, the electrons swing down and drop into that pi system. So if we evaluate the results on this, we have broken the pi bond, so I won't show that well. Here we can show the dotted line where that pi bond was. We have formed a new carbon-boron bond. We have broken the boron-hydrogen bond, and we have formed a hydrogen-carbon bond. Okay? So if we predict our product, the net, well, there it is. The net result is we've added that BH2 and the hydrogen across the double bond. Okay? We again run into an issue because we don't want boron on our compound, so we need to run a second reaction to cleave the boron off. The boron-carbon bond is relatively strong, so what we again need is something kind of fancy to get rid of it. That's where we bring in peroxide. Much, or in a potentially, at least the way I visualize it to help me remember the stereochemistry on it, what happens is our boron can accept electrons from the oxygen, which can kick electrons out to the other oxygen, which can kick electrons through, and everything comes out happy. Okay? The result is that if we look at the very, very end, the hydrogen and the OH were added on the same side of the double bond. This is a distinctly different result from all the other previous ones that we looked at. The tri-product, those ring structures where we had three-membered intermediate, produced trans alignment of the atoms being added across the double bond because we had that large electrophile atom that formed a ring, so that when the ring broke open, it had to break open where it was trans between the nucleophile and electrophile. Because we have this four-membered ring, both those pieces are coming in on the same side due to the stabilizing factor of the boron. So the result is we get a cis addition, or sorry, a syn addition of hydrogen and OH across a double bond in the case of the boron reagent. Okay? This does require two steps, because we first have to add the boron reagent to the alkene, then we have to remove the boron reagent from the alkene using a peroxide and hydroxide. Okay? So that's kind of how we stack everything together on that to end up with our final results. So I'm going to pause the video here again, and I might even let the clock run out a little bit to give you even more time to pause. Work on these examples, come up with the possible products on it, evaluate stereochemistry if you've got the time, and we will take a look at them in just a little bit. Have you paused yet? You should try pausing. Pause that video. Did you do it yet? Pause it. Okay. Is it paused? And we are back. You've got all the products shown out here. What I would highly recommend you do is compare these to what you came up with and evaluate the stereochemistry. If at any point you've got a question about any of the products shown, it could very well be possible I did something wrong, but I think I got them all right. Ask in class. feel free to start off class and be like, hey, I don't remember or I don't know how you got that product. Okay? And I will say that all of these products are things that I do expect you guys to be able to come up with, including the stereochemistry, based on the information we've talked about actually solely this semester. But if you apply stuff from first semester, you may be able to piece out and come up with where these products are coming from and potentially why. So some neat reactions going along with that. After that, we actually move into full-on chapter 24. The Diels-Alder reaction, another video will come up on Monday, maybe a little bit earlier, we'll see how I feel. And the other part of it is looking at really these three reagents, though it looks like it's a lot more than three. We're looking at osmium tetroxide, number 1, potassium permanganate, number 2, and then ozone, number 3. You'll notice that there's a lot more than just 3 reactions here. That's because if we change the conditions, we can get slightly different results in these. This is a particularly interesting reaction because the sequence of reactions are particularly interesting because they still give us this kind of cyclic intermediate as a primary driving force or driving factor within these. And further, if we push to the ozone and the hot concentrated permanganate, you'll notice that our ring structure cleaves open. So we can completely split a double bond. Kind of neat. The other thing that's fascinating within this is that you notice that we have drastically increased the number of oxygen bonds all the way through. That is kind of interesting and a little bit bizarre. So what we want to do is look at what's happening and why that is potentially occurring. In this case, what it is a redox reaction. So it may be helpful to understand or remember something about our redox reaction. Reduction is the gain of electrons. Oxidation is the loss of electrons. So we could look at a clear and obvious example like this one, and we can go, oh, that is totally a redox reaction because I can count the electrons on both sides and see that they've changed. Yes, that was sarcasm. That is not particularly obvious for most students. It is definitely not obvious for me. So when we move to organic chemistry, we want something a little bit easier than counting numbers. So what we'll do instead is count atoms, because that's more fun. So when we look at a reduction reaction, it is increasing the number of hydrogen bonds or decreasing the number of oxygen bonds. Oxidation is then the reverse. We either increase the number of oxygen bonds or decrease the number of hydrogen bonds. So depending on where we're looking, and most typically it's our organic compound, what changed as we went from our reactant to our product? Hopefully you notice that our carbons, at least 4 of them, picked up an extra hydrogen apiece. That means each of those atoms now gained a hydrogen, so we've increased the number of hydrogen bonds on my organic compound. We would classify this as a reduction reaction, which is counterintuitive to Gen Chem, because in Gen Chem we say redox. It's both. It is technically both. According to the organic species, it is a reduction reaction because we reduced the organic compound. Right? An important distinction and classification to make there. And that may very well be not quite, almost the last slide. We got a little bit more detail here with our penta intermediates. So we've got those same reactions drawn out there, and what I'm trying to show on the far left is that our reacting species is large enough that we can get to these larger transition states. So if we draw in an alkene, do I have that? There it is. What ends up happening is our alkene shares its pi electrons up with the oxygen. The metal takes the electrons from the oxygen, which then means the metal has an excess, so another pi bond breaks within that structure, and we can now form our 5-membered transition state. 1, 2, 3, 4, 5. One question you may ask, why would oxygen in that very first step accept electrons? Well, conversely, what you might be thinking, or a better way to think about that, might be to look at that metal. That metal has 4 electronegative atoms attached to it, all sucking electrons away. Eventually it says, piss off, oxygen, and it takes electrons from the oxygen to help satiate the other oxygens. Problem with that is that our oxygen now becomes extremely electrophilic, which is where our pi bond comes in to help initiate and facilitate the full reaction all the way around. If we transfer that information across to ozone, it's an even more or a easier process to see, because when we go through and evaluate what's going on with that, we have a positively charged oxygen in the middle. So what it does is start to suck on electrons. It could suck electrons out of this pi bond, which shuttles electrons up, shuttles electrons down. Okay? So we still end up with that 5-membered transition state. There's our 5 members in purple. So kind of a neat process. We will look at that in a significant amount more detail when we're talking about our osmium tetroxide, our permanganate, and ozone. One of the things that I will kind of caution you on is that ultimately these are really just memorization reactions. We'll talk about the details on what's happening within those mechanisms, but I'm going to try and burn through those in one lecture, because there isn't a whole lot that the mechanism adds to understanding. Okay? If you got questions, hopefully you watch this video, read the textbook, get some questions kind of worked up, so that when we come into class, you've got questions ready to go. Because if there aren't any questions, and even if there are questions, I may fire a quiz at you regardless. Okay? So, good luck. Let me know if you've got any questions when they pop up.